Okay, we have shown in the last lecture that we can approach this rate region for the Gelfand-Pinsker problem. So the difference between the mutual information of u and y and the mutual information of u and s. We have to show now the converse. But before that, I want to remind you, we already looked last time at some special properties. So you see, I can write this difference also in this way. If I estimate here the entropy by adding here a condition. So you see, if both the encoder and decoder have access to Sn, then we have here an equal. That means we can achieve this rate here if the encoder and the decoder have access to Sn. The next thing where we look at it was if y is independent of S, given X. And then it's not surprisingly, we get the same capacity as we get for the channel without state. Now let's come to the converse. For the converse, we need again some convexity property of the rate. So if you look at this function as this difference here, which depends on the probability of S, U, X, and Y, and we look at this distribution. And then we assume that PSU and PY under the condition SX is fixed. But if these probabilities are fixed, then this mutual information is also fixed. But we know if we have just one mutual information, then we know it's already a convex function of PYU and PU. And with this property, we can show that this rate is also convex. Now we want to come to the converse. So first we want to apply the Fano inequality. Perhaps it's not obviously why this follows. Therefore, I will write it down. Okay, we want to look at a channel with average error probability. That means we can assume that every message has the same probability. But then we know that the cardinality of all messages, which is W, is equal to the n r. And now if you look at the entropy, and all have the same probability, that means all have the probability 1 over 2 to the nr, then this, in this case, this entropy is equal to nr. Now let's look at Fano's inequality. Fano's inequality says that the binary entropy of the error plus the probability of the error times the logarithm of the cardinality of the alphabet is greater equal than the entropy of W and conditional on W hat. Now we know that this cardinality of W is 2 to the nr, so we can insert here n times r, so we have here h2 of the error probability plus PE times n times r. And now here we write it a little bit more complicated. We write it as the entropy of W minus the mutual information of W and W hat. Yes, you see, if you just plug in here for the mutual information, it's equal to H of W minus H of W under the conditional W hat. You get exactly what we have here. Now, if you put this together, what do we have? We have now, if you put this to the other side, then we have that the mutual information between W and W hat is greater equal than Now we put in for h of w, we put in n times r minus the error probability times n times r minus the binary entropy of the error. But this we can write now in this form. We just can write this as n times r times 1 minus PE minus h of 2 of PE, where PE denotes the error probability, and we know that PE goes to 0, and therefore we have that the mutual information of W and W hat is greater or equal than n times r. Okay, let's go back to the slides again. So here we have already our estimation. Now we apply the data processing lemma. So that means the mutual information between W and W hat is less or equal than the mutual information between W and Y to the n. Next, this is a trick of Gerd Kramer here from our institute. It's a new proof. Gelfand Pinsker used another proof. It's some kind, it's called telescope equality somehow. The trick is here to insert here the sequences of random variables such that Sij denotes Si times Si plus 1 until times Sj, and we assume that Y0 is equal 0. Then we can write this mutual information with this sum here. If you write this out, then you will see that everything canceled out at the end, and you are back with this mutual information. This is just a trick just to expand this mutual information here. Now, we apply now to this the chain rule. So you see, instead of this is the first term, this is the chain rule of the first term of the sum, and this is the chain rule of the second term of the sum. And the nice thing now is, if you look, that this term and this term canceled out, and we are just left with these two terms here. These two terms we write now in the forms of entropy, and furthermore, we set ui equal w times sni plus 1 times y to the I minus 1. Then we got this equation here, then we get this here. So we write for this, we write it in entropies, the formula of this mutual information, and this in entropies, and then we put ui equal to this, and then we get this equation here. Now we know that Si is independent of W and Si plus 1 to n. That means we can write here only the entropy of Y, and here we can write the entropy of Si. Now, if you look at these two terms, this is just the mutual information of Ui and Yi, and this is just the mutual information of Ui and Si. And then we can bound the sum by n times its maximum in terms, and so we know that the rate is less or equal to the maximum over all i's. So here you see, again back, here we have for I equal 1 to n, and then here each term, and we know that n times r is less or equal than this. And now we just take here the maximum over all i's. And of course, this we can write also in this form, and therefore the rate can be estimated, the rate must be smaller equal to this. Just notice this n cancelled out. Here we have this n, and here we just take the maximum over all i's. And then we have n times the maximum over all times, and we cancel out this n and this n, and then we remain with this thing. And therefore, we have proved the converse of Gelfand-Pinsker.